And now, please welcome Mark Kempton from Brigham Young University, who's going to talk us about fractional revival and generalizations.
All right, thank you, Maria, and thank you very much to the organizers for the invitation to be here. I feel like it's been really a fantastic workshop so far, so it's really an honor to be part of this. Just to give you a little outline of what I'm going to talk about, I'll start off with some background on quantum walks and perfect state transfer. That will probably be a lot of repetition of things that we've seen in other talks already. And then I'll talk about a generalization of perfect state transfer called fractional revival, and some of the spectral framework developed around fractional revival. And then we'll take a look at two generalizations of fractional revival, something we call K-Fractional Revival, and also pretty good fractional revival. All right, so to start off, we've seen a lot of people talk about quantum walks on graphs, so I won't dwell a lot on this, but a quantum walk is this process governed by this unitary transition matrix. I think there's technically supposed to be a minus sign in front of the t, but the math all works out the same, whether that's there or not. This is always a unitary matrix, as long as we're working with a Hermitian matrix up here. And for purposes of this talk, we'll think of this as the adjacency matrix of some graph. And physical interpretation, I'm no physicist, but I think of, since this is unitary, each row and column is a unit vector. So I think of this as representing probabilities. The absolute value squared of each entry represents a probability of your quantum walker being at any particular vertex at any time t. All right, so a big question that has gotten studied quite a lot about quantum walks is this question of perfect state transfer, which we'll abbreviate with PST. So we say that there's perfect state transfer if the absolute value of this transition matrix at its UV entry is equal to 1. So think of this as starting at the vertex U and traveling with probability 1 to vertex V at time t. Now, a perspective that at least for me helps a lot of what we're going to talk about be more intuitive is to look at your actual U of t matrix. Now, U of t is a unitary matrix. So if one of its entries has absolute value 1, well, if the rows and columns are supposed to also have norm 1, that means that you have, if my first two rows and columns of this matrix are indexed by the vertices u and v, then I'll have a single entry in the UV and VU entries that's not 0, and the rest of those rows and columns are 0. So perfect state transfer implies that at this particular time t, my U of t matrix has this nice block decomposition, where in this upper corner, I have this particular matrix. Alpha here is going to be some unit modulus complex number, and then some other unitary matrix for the rest of the vertices. Okay, so looking at it from this perspective, you can ask, well, what is needed? When can this perfect state transfer happen? And of course, the eigenvalues and eigenvectors of my e to the ita matrix, well, any eigenvector of my adjacency matrix is going to stay an eigenvector of e to the ita, right? And any of the eigenvalues, right? So if I take an eigenvector of the adjacency matrix, I'm going to get e to the it lambda times that same eigenvector. So we can see that e to the it lambda for lambda, an eigenvalue of the adjacency matrix, becomes an eigenvalue of this U of T matrix, and it corresponds to the eigenvector of the adjacency matrix is a corresponding eigenvector. Now, if this is a block diagonal matrix, then in particular, if I restrict this to these first two entries, then what that tells me is that this e to the it lambda must be an eigenvalue of my 0 alpha alpha 0 matrix corresponding to the restriction of the eigenvector to those two vertices. Well, okay, what does that mean? Well, this matrix has a pretty specific structure, right? Its eigenvalues are going to be 1, 1, and 1, -1, or any multiples of those. And its eigenvalues are going to be plus or minus alpha. So if I want perfect state transfer to happen in my graph, then I need the restrictions of my eigenvectors of the adjacency matrix to be multiples of one or the other of those vectors. And all of the eigenvalues, if I take e to the it lambda, must satisfy that it's plus or minus some unit complex number. So requiring perfect state transfer imposes a condition on the eigenvectors of the adjacency matrix and on the eigenvalues of the adjacency matrix. So let's keep that in mind. So this leads us to cospectrality. Now, the definition of cospectrality looks a little different from what I was just talking about, but this actually follows from the condition on the eigenvectors. So two vertices of a graph are said to be cospectral if they have the same characteristic polynomial when you delete each successive vertex. So spectrally speaking, the eigenvalues of the adjacency matrix can't distinguish these two vertices. Cospectral vertices have been studied really a lot. A few statements in particular that are equivalent to two vertices being cospectral. So we have the definition that the characteristic polynomial of my two vertex deleted graphs is the same. This is equivalent to the UU entry and the VV entry of the spectral idempotence in the spectral decomposition of the adjacency matrix being the same for U and V. This is equivalent to there existing a basis of eigenvectors of A such that the eigenvector evaluated at U is either the same as at V or opposite at V. Or in other words, the restriction of these eigenvectors has to be a multiple of the 1, 1 vector or the 1 - 1 vector. So this is relating back to the condition on eigenvectors that our perfect state transfer was imposing. And a more combinatorial way of looking at cospectrality is that if I count closed walks at the vertex U and the vertex V, I'll get the same count for any value of K. So here we're taking the kth power of the adjacency matrix, and as we know, that counts walks starting and ending at U of length K. All right, I could add lots of things to this list if I wanted to. There are really very many characterizations of cospectrality in a graph, but these will be sufficient for what I'm going to talk about today. And then, of course, a strengthening of this, and we heard Chris talk about this yesterday, strong cospectrality is when the uth column of your spectral idempotent is always plus or minus the vth column of the spectral idempotent. Equivalently, every single eigenvector will satisfy phi of u equals plus or minus phi of v. So cospectrality only required this for some fixed basis of eigenvectors of the adjacency matrix, When you have strong cospectrality, you need this to be true for every single eigenvector. So it's possible, if you have some eigenvalue multiplicity, to have this cospectrality satisfied without strong cospectrality. But strong cospectrality, as we mentioned, is a necessary condition on the eigenvectors for there to be perfect state transfer between U and V. So perfect state transfer will occur if and only if these two conditions are satisfied. So we have the condition on the eigenvectors that I mentioned, strong cospectrality, and we also have the condition on the eigenvalues. So you need every single eigenvalue to satisfy so when I have strong cospectrality, this naturally groups the eigenvalues into two groups, right? I have the eigenvalues for which the eigenvector is constant on the two vertices and the eigenvalues for which it's opposite on the two vertices. And like I said before, the e to the it lambdas have to be eigenvalues of my 2x2 matrix, 0, alpha, alpha, 0, when we looked at that block decomposition. So within the one group on that grouping, e to the it lambda has to be constant. And if I take an eigenvalue from the other group, when I take e to the it lambda, it has to be opposite that value. Okay, so this is a characterization of perfect state transfer in terms of this condition on the eigenvectors and a condition on the eigenvalues. If you look at the condition on the eigenvalues, if you take, I won't go into this in detail, but if you take logs of both sides here, subtract things over and move things around a little bit, you get what's called the ratio condition. And I believe Chris brought this up in his talk yesterday as well. So within these groups given by the strong cospectrality, your eigenvalues must satisfy the ratio condition. So this ratio of differences of eigenvalues must be a rational number for any eigenvalues within the same group. So keep that in mind. This ratio condition is necessary for perfect state transfer. Okay, so with all that under our belts, let's look at, oh yeah, a very good question in the chat. One detail that I'm brushing under the rug here is that everything I've said only applies to the eigenvalue support of the vertices, right? So if I have an eigenvector that restricts to 0 on those two vertices, then I can kind of ignore that. I don't need the ratio condition there. Good, thank you. Okay, so fractional revival is a generalization of perfect state transfer. So perfect state transfer was that the absolute value of the UV entry was equal to 1. Fractional revival says that the sum of the absolute value squareds of the UU entry and the UV entry add up to 1. Okay, so again, my U of T matrix is a unitary matrix. So if in 2 of the entries, if those are already accounting for the full probability, that means the rest of the entries in those rows and columns have to be 0. So fractional revival means that in my unitary transition matrix, I again have a block decomposition. Again, these first 2 rows and columns are indexed by the vertices U and V. But now I'm allowing any symmetric unitary matrix to show up in this upper left corner. And then I'll, again, just have something else down on the rest of the vertices. So, of course, perfect state transfer is an example of fractional revival in which these 2 diagonals are 0 and those both have absolute value 1. Okay, so from this perspective, a lot of the same theory that we talked about transfers over in a lot of ways, just with a more general matrix right here. So once again, if I take an eigenvector of the adjacency matrix, this will be e to the it lambda times that same eigenvector. So if I look at that restriction to those first two entries, then the restriction of the eigenvectors must be an eigenvector of this unitary matrix right here. And my e to the it lambda must be an eigenvalue of that unitary matrix. So once again, we're seeing fractional revival impose a condition on the eigenvectors of the adjacency matrix and on the eigenvalues of the adjacency matrix. But it's a little more general. There's not one specific matrix here that it has to satisfy. There just has to be some unitary matrix for which this is satisfied. There's a paper written by, well, several of the organizers of this workshop back in 2019 that studied fractional revival in graphs. They came up with lots of examples, lots of properties. All the examples they came up with in that paper of fractional revival just happened to have strong cospectrality between the vertices on which there was fractional revival. So a big question from that paper is, well, can fractional revival happen between non-cospectral vertices, and what's the theoretical framework there that we have? And this paper, I think, sparked a lot of people thinking about this, and I think a lot of us thought about it independently, and then we had a workshop at Waterloo in 2018 where we all kind of realized that we were thinking about some of the same things, and we ended up writing a paper with lots of authors on it about a lot of these things, but I'll get to that in just a second. So the eigenvector condition is something that we're going to call strong fractional cospectrality. So we're, at the risk of putting too many adverbs before our adjectives, we say that U and V are strongly fractionally cospectral if all of the eigenvectors of A restricted to vertices U and V are eigenvectors of some 2x2 unitary symmetric matrix. So in other words, I can find some numbers P and Q such that the restriction of the eigenvector, so this tilde above the eigenvector denotes restricting the eigenvector to the two entries corresponding to U and V. So if I can find two numbers P and Q such that every eigenvector will restrict to either PQ or minus QP, then, and if those are eigenvectors of this 2x2 matrix, unitary matrix, then we call that strong fractional cospectrality. So just to point out that this is a generalization of strong cospectrality. So strong cospectrality is just an example of this where P is equal to Q. All right, so first theorem to mention that's kind of immediate, and this paper ended up having, I think, 9 co-authors on it, and my apologies for only listing the initials here, but if I tried to write them out, I don't think they'd fit on the slide. But proper fractional, what do I mean by proper here? So if I allow this to just be the identity matrix, then of course I'm not imposing very many restrictions on the eigenvectors because, well, most vectors are eigenvectors of the identity matrix. So we're going to say that the fractional revival, did I remember to say this back here? It doesn't look like it, but I'll say that the fractional revival is proper if this is not just a diagonal matrix. So if this is diagonal, then that just means that the two vertices are periodic at the same time. That's not so much what we're interested in here. So proper fractional revival will occur between vertices u and v if and only if the vertices u and v are strongly fractionally cospectral vertices. And once again, the strong cospectrality, or the fractional cospectrality, groups the eigenvalues into two different groups. So you have the ones for which the restriction is PQ and the ones for which the restriction is minus QP. And the eigenvalue condition amounts to the eigenvalues within each group satisfying the ratio condition that we saw before with perfect state transfer. Okay, so we have a nice spectral framework in which we can study fractional cospectrality. As soon as you look at that, you start to wonder, okay, I have strong fractional cospectrality that corresponded to strong cospectrality in perfect state transfer. Now, strong cospectrality was a strengthening of the notion of cospectrality. Is strong fractional cospectrality any kind of strengthening of some weaker condition that's analogous to cospectrality in some way? And the answer is yes. So if you take a look at the spectral decomposition of your matrix, it turns out that each of these statements here is equivalent to each other. So if I look at the UU and VV entries of my spectral idempotents, now with cospectrality, those were equal to each other. With what we call fractional cospectrality, the necessary condition for fractional revival only requires that those be this constant times the UV entry of your spectral idempotent. And this has to be true for each R. With cospectrality, we needed the existence of a basis of eigenvectors for which phi of u was plus or minus phi of v. Now phi of u is just going to be some constant times phi of v, or negative the reciprocal of that constant times phi of v. We can characterize this combinatorially as well, just like with cospectrality, the Watt counts at u and v were always equal. With fractional cospectrality, the Watt counts have to differ by some constant times the Watt counts between u and v. And finally, you can tell this by looking at the characteristic polynomial as well. If you look at with cospectrality, the vertex deleted characteristic polynomials were equal. With fractional cospectrality, they differ by a constant times this polynomial phi sub uv. Now, I haven't defined phi sub uv, and well, I don't think I'm going to define it, but it's this polynomial that comes up a lot in the study of cospectral vertices. And you can get it by looking at your determinant of a minus lambda I and deleting row u and column v. But anyway, you can characterize it. So all of our statements that we're characterizing cospectrality have an analogous statement for fractional cospectrality that are all equivalent to each other. So any one of these statements you could take as a definition for fractional cospectrality. Strong fractional cospectrality is a strengthening of this, which was our necessary condition for fractional revival. All right. So, okay, so once we've developed this, spectral framework for studying fractional revival, what can you do with it? And I guess the first answer is you can come up with examples. And one of the first questions we asked was about this monogamy property. So back in 2011, Alistair Kay proved that perfect state transfer is monogamous. So if I have perfect state transfer between two vertices in a graph at some time, and then I have perfect state transfer between U and W at some time, then V has to equal W. So perfect state transfer has to occur in pairs. I can't have perfect state transfer from one vertex to two different vertices at different times. We call this the monogamy property of perfect state transfer. So one of the big questions from this 2019 paper that I referenced earlier was, does fractional revival satisfy this same monogamy property? Could you prove the same thing about fractional revival? And it turns out that the answer is no. So here is an example. So with the spectral framework that we've developed, how can you construct examples? Well, you want this condition on eigenvectors and the condition on eigenvalues. So what we did here is we chose the eigenvalues that we wanted. So you choose the eigenvalues carefully so that you'll get the ratio condition that we had before satisfied at various different times. This H matrix, I haven't told you what it is. H here is a Hadamard matrix. So its entries are all plus and minus ones. So you actually have strong cospectrality here. The entries of H are going to be the eigenvectors of my matrix. And you just take that to be the diagonalization of the matrix that you want. So you multiply all that out and you get this matrix here, which just happens to be a weighted Laplacian matrix. So if you take this matrix and take e to the it times that matrix, well, if you look at it at time 2 pi over 3, you get this block decomposition that we like. If you look at it at time 2 pi over 5, you get, well, something that you could permute to a block decomposition, and same at 2 pi over 7. So really you have fractional revival here between every pair of vertices in this graph. So you'll notice the denominators here are all prime numbers, and that's not a coincidence. So basically to come up with these eigenvalues, we're looking at can my ratio condition be satisfied at different times? And so we made use of the Chinese remainder theorem to, you know, if your time has this prime number, then you can find eigenvalues that will satisfy the ratio condition at those different times. Okay, so I think that's interesting that in some sense, fractional revival is very different from perfect state transfer in that regard, that you don't have the monogamy property here. All right. So now we'll move on to something we called K-Fractional Revival. And I'll be honest, I don't know how interesting this is to the physicists. It probably is pretty interesting to the physicists, but as a mathematician, when you've used a tool, you can't help but generalize it. So the tools we were using were all kind of falling out of this block decomposition of the unitary transition matrix, our quantum walk matrix. And so as a mathematician, you ask, well, what was special about the block decomposition having a 2x2 block? And from the mathematician's perspective, there's nothing really all that interesting about that. So we generalize this to say that if I take any subset of the vertex set of my graph, we'll say that there's K-fractional revival if my quantum walk matrix at some time t has this nice block decomposition into two blocks, where this upper left corner here is what's indexed by the vertices of K. So H here will be some symmetric unitary size of K by size of K matrix.
We have one question.
Oh, yeah.
In the chat. What happens at twice the time of fractional revival?
Oh,
is it periodic in those two vertices? And those
going back to this, so if I double the time, will I get periodicity between those two vertices? Now I don't remember. I don't think so necessarily. Because, well, yeah, right. Because if you square this, you're not necessarily going to get the identity. When there was perfect state transfer, when you square your 0 alpha alpha 0, then you will get a multiple of the identity there. But that's not necessarily the case with your fractional revival. Okay, great. And Ada has an example for us. Okay, so that's a good point in the chat too. All your amplitude is still within that subset. Yeah, I think that's right. If you double this time, you'll still have fractional revival at the multiples of that time. Yeah. Okay. Okay, so back to K-fractional revival. Again, we'll call this proper if H is not a diagonal matrix. So if it's not just corresponding to periodicity at all of the vertices in the subset. And so, of course, everything that I said before, you can say in this situation too. It's a little bit more subtle. So if I know the matrix that I want to put here, then everything we said in the 2x2 case carries over, right? Every eigenvector of the adjacency matrix must restrict to an eigenvector of H, and the eigenvalues, when I exponentiate them, have to be eigenvalues of the matrix H. Now, it gets a little more subtle when it's not 2x2, when you're not necessarily prescribing the H here. You just want to talk about the existence of some unitary H that works. But the theorem that we can write down, if you look at the partition of the eigenvalues, the minimum partition of the eigenvalues based on the subset K, you can partition your eigenvalues based on that. And if the eigenvalues satisfy the ratio condition for within each part of the partition, of that partition, then you will have, there will exist some K by K unitary matrix that will work. So you'll have this generalized K-fractional revival in that situation. Okay, so you can use that framework to start coming up with examples. And we have some examples based on products and double covers and joins. I won't go into any details on those, but you can look up some of those examples in the paper. Okay, so that brings me to pretty good fractional revival, which this was motivated by the notion of pretty good state transfer, which was introduced by Chris Godzel in 2012 and some others, which is an approximation of perfect state transfer. So we say that there's pretty good state transfer if the absolute value squared of your UV entry is at least 1 minus epsilon. Sorry, so for every epsilon, there is a T such that this absolute value is at least 1 minus epsilon. Pretty good state transfer has also been studied pretty extensively. The eigenvalue conditions become a lot more subtle here. So I'm not going to go into a lot of detail on this because I don't have very much time left, but there's some number theory tools that you can use to analyze the eigenvalues. strong cospectrality is still necessary for pretty good state transfer. And there's this very complicated condition on the eigenvalues that if you look at these integer linear combinations of your eigenvalues such that those integers add up to 0, then the sum of those integers within any one of the groups has to be even. So it takes a lot of number theory to analyze that, but that ends up being the condition. So it's very natural to then ask, let's look at the same kind of approximation for pretty good fractional revival. So we'll call that PGFR. And you can do the same kind of number theoretic analysis. It turns out that strong fractional cospectrality is still a necessary condition for PGFR. And then we get a very similar condition on the eigenvalues, where if you look at these integer linear combinations of the eigenvalues, then now the only condition is that the sum of the mi's not be plus or minus 1. So before this had to be even, now we're just requiring it that it not be plus or minus 1. Very natural first place to start studying fractional revival is in paths. So perfect state transfer and fractional revival and pretty good state transfer have all been widely studied in paths. PST only happens if the length of the path is 2 or 3. Fractional revival occurs if and only if the length of the path is 2, 3, or 4. And then a sequence of papers characterized pretty good state transfer in paths, where there's PGST if and only if the length of the path is a power of 2 times a prime minus 1. All right, so work that we did on paths. So the first question to ask is, when can fractional cospectrality happen in a path? Of course, cospectrality is an example of fractional cospectrality. So between any symmetric pair of vertices in a path, you have cospectrality. And then we found this interesting case that if the path happens to have length 5d minus 1, then, and I'm labeling the vertices 1, 2, 3, up through 5d minus 1, then it just so happens that between vertex D and vertex 3D, those vertices are fractionally cospectral. We proved this by looking at the walk count conditions. So when it's a path, it's not too hard to think through the combinatorics of how many closed walks are there at any given vertex, and you can determine when in a path you can have this fractional cospectrality. And then the result about PGFR is that PGFR in a path occurs if and only if you have PGST. Of course, PGST is an example of PGFR. So the situations characterized previously for PGST are still examples of PGFR, of course. And then we get a few other situations. So if the length of the path happens to be 5 times the power of 2 minus 1, then I get PGFR between these two nodes. I don't know, I think that's kind of mysterious still. You can work through all the math of the eigenvalues and prove it, but I think it's very interesting that that little relaxation allows for these kind of non-symmetric situations where you get this pretty good fractional revival. Okay. In the same paper, we also looked at cycles. The situation with cycles, the fractional cospectrality was maybe a little less interesting with cycles So the only cases where you have strongly fractionally cospectral vertices and cycles are when they're actually strongly cospectral. And so we were able to characterize when PGFR occurs in cycles, and it occurs if and only if the length of the cycle is 2 times a prime power, and the PGFR occurs across antipodal vertices of the cycle. Okay, so that's a summary of a lot of the work that we've done. Some avenues for future research. Of course, more examples are always interesting. Some of my colleagues and I have a lot of work looking at PST and PGST in the presence of a diagonal potential. So if you add some diagonal to the entries, can that help you get PST or PGST? We would find it interesting to generalize that work to fractional revival and pretty good fractional revival. I would find it very interesting to understand this non-monogamy property better. So in the example I showed you, we had 4 vertices, and you had this fractional revival between every pair of vertices at different times among those 4 vertices. So I think it would be interesting, and maybe someone already knows this, but could you have some subset containing only 3 vertices where you have pairwise fractional revival between any 3 of those vertices, but not a 4th vertex? I don't know if anyone has studied that yet, but can we get a better understanding of this non-monogamy? And then in the big 9-author paper that we talked about, we do have an example where it's not necessarily block diagonal, but you do have a situation where you start at a particular state and then it moves to at a certain time to something concentrated on other vertices, but not including that original vertex. So that kind of thing may also be interesting to study. But I think I'll go ahead and stop there.
Thank you for the talk, that's famous speaker.
Thank you. I'll maybe try to get caught up with the chat here. and yeah,
it started with the question, do you have analytic models that project to chains of arbitrary dimension?
Analytic model that project to chains. I guess I'm not totally sure what's meant by that.
Well, I'm not the author.
So he just means if you have fractional revival over 3 vertices in a weighted path.
Oh, so in chains. So do we have larger subsets in paths? No, we haven't studied that yet. And I certainly think that would be interesting. That's definitely another avenue of research that I could add to that list there.
Are you looking for something like a distance regular graph with fractional revival on 3 vertices, or actually on the path, on the quotient?
Yeah, looking at so I think my answer to most of these questions is I don't know, and I suspect it's not known yet.
As I was saying in the chat, it would mean very new properties regarding orthogonal polynomials that are associated, that are forming this tridiagonal system.
Right.
And so this is why I'm asking if somehow by going up on the graph and through your methods, if you could, you know, get a projection, a weighted path that would have this property. Would be very curious about what it would look like.
Right.
And in the same vein, it's a question I have, because in the first studies we did, it was a very special, or, you know, very unfamiliar family of orthogonal polynomials that we've called para-Kraftwerk polynomials. And this is quite similar to projecting the hypercube down to the path where you get the Kraftwerk model. But these polynomials are inherently connected to fractional revival. And I don't really know to what they lift.
Mm-hmm.
Alistair commented something.
Yeah, Alistair may have at least a partial answer.
Yes, but Alistair, is it, you have analytic closed form? This is what would be, you know, quite interesting from the point of view I'm bringing. Of,
to be honest, I don't remember. I think there were little bits of it I could do analytically.
Okay, I'll look it up.
Yeah.
Thanks.
So if there are questions, let's English speak.
Thank you.